Hello everyone, I'm Professor Harrison, and welcome to our module on calculus for optimization. In this video, we're going to be covering what a derivative actually is. We'll build up the intuition for why you'd want one, walk through the core idea of an instantaneous rate of change versus an average rate of change, and cover the notation that you'll see throughout this entire module. Throughout this module, we're going to be following a character named Victor Callaway. Victor is a fund manager, and he runs a fund called Callaway Value Partners. For most of Victor's career, things have been going well. His models have been working and his returns have been solid. But recently, something has changed and his edge has started to disappear. His positions aren't performing the way they used to, and he can't figure out why. Then one day, a letter shows up at his office. It's from someone he's never corresponded with before. The letter is from a manager of a competing fund called the Rational Quant. And the Rational Quant says they've noticed Victor's recent drop in performance. They're writing to offer advice. And Victor doesn't know why a competitor would do that, but the letter is precise and the math is clean. He opens up the letter from his anonymous correspondent. Before we can talk about optimization, we need to build a tool. And that tool starts with a single question. How fast is something changing right now? That's a different question from how fast something changes on average. And the difference between those two ends up being one of the most important distinctions in all of quantitative finance. So let's start with an example. Think about a company that sells a product. As a company raises the price, fewer people buy it. So, total revenue depends on the price the company charges. And at low prices, raising the price brings in more money because you're earning more per unit sold. But at some point, the price gets high enough that it actually drives away so many buyers that the total revenue actually starts to fall. So, the demand is going to change depending on what the price is. Let's say that we can actually quantify what the demand will be given a certain price. For example, we can say that the demand as a function of price works out to 1,000 minus 10 times the price. So for example, at a price of $20, 1,000 minus 200 gives you 800 units sold. At $50, demand would drop to 500 units. Using this, we now can calculate what our revenues are going to be. Revenue is just price times quantity. So revenue as a function of the price is just going to be the price times 1,000 minus 10 times the price, which simplifies to 1,000 times the price minus 10 times the price squared. So at a price of $20, revenue ends up being $16,000. At $30, revenue would then be $21,000, and at $40 it'd be $24,000, at $50 it'd be $25,000, which turns out to be the peak. At $60, revenue would actually start to drop back down again to $24,000. So here's the question. You're currently charging $30. You want to know, if I raise the price a little bit, does revenue go up or down, and by how much? One approach is to just look at the average rate of change. From a price of $30 to a price of $40, revenue goes from $21,000 to $24,000. That's a change of $3,000 over a $10 price increase. So on average, revenue went up by $300 for every $1 increase in the price. But that average is spread across a pretty wide interval. The rate of change might not be constant over the whole range. So what if we narrow it down? Instead of going from 30 to 40, let's say we go from 30 to 31. So revenue at $31 ends up being $21,390. So the change is $390 over a $1 price increase. And that gives us an average rate of change of $390 for every dollar price increase. So why exactly are we getting a different answer here? Both of these things start at $300 and we're getting different rates of change. When we use a $10 interval, we got that the rate of change was $300 per every dollar of price increase. But over the smaller interval, we got $390. Two different numbers. And the narrow interval is giving us a more precise picture of what's happening right at the price of 30. What we can do is shrink this even further. So instead of going from 30 to 31, we could go, for example, from 30 to 30.1. Revenue at 30.1 ends up being around $21,039.90. That's a change of $39.90 over a price change of 10 cents. So the average rate of change is $399 per dollar price increase. You can see the pattern here. As we make the interval smaller and smaller, that ratio keeps settling in closer and closer to 400. And that's the key idea. The derivative is the value that that ratio converges to as the interval shrinks all the way down to zero. The derivative of revenue with respect to price, evaluated at price of 30, is 400. This means that right at a price of $30, every tiny little increase in price adds roughly $400 to the revenue. So let's formalize exactly what we've been doing. The thing we've been computing each time is called the difference quotient. It's the change in the function divided by the change in the input. If we call the function f and the input x, and the width of our step h, then the difference quotient is f of x plus h minus f of x all divided by h. That ratio gives you the average rate of change over an interval of width h. The derivative is what the ratio converges to as h goes to 0. We write that as the limit as h approaches 0 of f of x plus h minus f of x divided by h. Now, mathematically, this seems a bit confusing at first, but let's take a look at what this would look like graphically. If we look at the geometric picture, we can make the whole thing really click. If you plot the revenue function, you get a curve. What we are basically doing is picking 2 points on the curve, one at price of 30, for example, and one at price of 40. All we're doing is drawing a straight line through these 2 points, and that line is called a secant line. And the slope of that secant line is exactly the average rate of change that we just computed. We found that the average rate of change was $300 per dollar increase in price. Let's see how that would map to our function for the average rate of change. In our function, x in this example is going to be 30, and the width of our interval, h, is 10. We evaluate f of 30 plus 10 minus f of 30 all divided by 10, and that's 24,000 minus 21,000 divided by 10, giving us the exact same $300 per dollar price increase. Now let's see how this changes as we slide that point closer and decrease the size of our interval h. If we move it from 40 down to 31, the secant line tilts. Its slope is now 390. If we slide it to 30.1, the slope is now 399. As the second point gets closer and closer to the first, the secant line sort of rotates until it's just barely touching the curve at the single point. That line is called the tangent line, and the slope of the tangent line is what we call the derivative. So the derivative has two perfectly equivalent interpretations. It is the instantaneous rate of change of a function at a specific point, and it is the slope of the tangent line to the curve at that point. The same number, just two different ways of looking at it. Now let's talk about what the sign of the derivative actually tells us. At a price of 30, the derivative is 400. That's positive, so revenue is increasing at that point. So that means that raising the price a little bit would bring in more money. At a price of 50, the revenue hits its peak, and the derivative there is 0. At this point, the tangent line is perfectly flat, so revenue is neither increasing nor decreasing at that instant. And at a price of 60, the derivative ends up being negative 200. This means that revenue is falling, so raising the price past that point would actually lose you money. So the derivative doesn't just tell you the rate, it tells you the direction. Positive means the function is going up, and negative means it's going down. 0 means it's flat right at that point, and when the derivative switches from positive to negative, you found the peak. We'll get into exactly how to use that for finding optimal points later on in this module, but the intuition is already here. So the last thing we need to cover is notation. You'll see the derivative written out in two different ways throughout this course, and they basically mean the exact same thing. The first is called prime notation. If the function is f of x, then the derivative is written f prime of x, and the prime mark just means that we've taken the derivative of the function. So for example, f prime of 30 equals 400. This means that at 30, if you were to slightly increase the price, then you would increase the revenue by approximately 400 times however much you increase the price. The second way that we write it is called Leibniz notation. It writes the derivative as df over dx. This notation looks like a fraction, and that's actually intentional. It's reminding you that the derivative came from a ratio. The change in f, aka d of f, divided by the change in x, aka d of x. Then we just take the limit of it. When you want to evaluate the derivative at a specific point, you can write f prime of 30, or you can write df over dx with a vertical bar and x equals 30 next to it. Either way, you're saying, give me the instantaneous rate of change of f evaluated right at x equals 30. Both notations end up being useful in practice. Prime notation is compact and clean when you're writing out formulas. Leibniz notation is better when you want to keep track of what's changing with respect to what. And that distinction ends up being especially important once you get into functions with more than one input. Victor sets his letter down. The first thing he does is pull up Callaway Value Partners' net asset value over the last 4 years. The fund started at $100 million. It's sitting at $160 million right now. That's a $60 million growth in the last 4 years. So the average rate of change is 15 million per year. But that average is hiding something. Last quarter, the fund went from 158 million to 160 million. That's $2 million in a single quarter, which works out to roughly $8 million per year. The average says $15 million per year. The current rate says 8. The fund is still growing, but it's decelerating in its growth. And the 4-year average return that he's been reporting to investors doesn't show that at all. The derivative gives Victor something the average completely misses. Not where the fund has been on average, but where it's heading right now. The trajectory is bending downward, and he couldn't see it until he had this tool. Victor didn't ask for this letter. A competing fund manager noticed his performance slipping and reached out unprompted. He's not sure why someone would do that, but the math in the letter was sharp and the tool it gave him is already showing him something that his own models missed. So he decides to write back. So that's what a derivative is. It's the instantaneous rate of change of a function at a specific point. You get there by computing the average of change over smaller and smaller intervals and watching what the ratio converges to. Geometrically, it's the slope of the tangent line. The sign tells you the direction, with positive meaning increasing, negative meaning decreasing, and zero meaning there's no rate of change. And you'll see it written as f prime of x or df over dx. This ends up being the foundation for everything we'll do in optimization going forward.